1. So what we're going to do is we're going to produce a series of mind maps, really, so some of the key points from each spec point, which should hopefully help you with your revision this evening, ready for tomorrow morning. So starting with spec 1, so put spec 1 in the middle. Now, first thing for spec 1, the first part that you cover, elements, compounds and mixtures. So these are 3 words that you need to understand the definition for. It's got elements, compounds and mixtures. So starting with elements, they only contain one type of atom. A mixture is, a compound is 2 or more elements bonded together. And then you've got a mixture, which is 2 or more elements or compounds not bonded together. Now, in order to separate these, you have a series of, so first one you've got is distillation, or one of them is distillation. That's where you're separating 2 different liquids that have different boiling points. Then you've also got fractional distillation, which is where you've got several liquids, all again with different boiling points. So easy to remember distillation and fractional distillation, because ultimately it all works on that property of boiling point. Bigger. Another separation technique you've got is chromatography. This one is one size what, yeah. Filtration, which is where you'd filter out an undissolved solid from a liquid, and you also have crystallization, which is where you separate dissolved solids from liquids. So you need to understand these 3 definitions in order to separate, particularly if you've got maybe a mixture of some compounds, then you might use one of these different separation techniques. So in year 9, that's probably covers about roughly a third of your lessons at the beginning of the year. Then after that, you start to look at the history of the atom and atomic structure. So we'll put atomic structure over here. And this is the sort of fundamentals, really, which helps you with all the different spec points for paper 1. In atomic structure, you need to understand the history of the atom. Now, there are 5 scientists that you need to be aware of. Underline, because he's the only one where you have to understand what he did. So each scientist, you need to understand the discoveries, but for him, you need to understand what he did. Now, what he did was the gold foil experiment. Electrons are in shells, and you also have Chadwick, who was on the separates paper last year. In a small way, he discovered neutrons. So they're your 5 scientists. Now, after the work that those 5 people did, we then have the atomic model that we use now. So I'm going to draw helium. Now, in order to do that, you'd find helium on your periodic table, which is He, and you'd notice that its top number is 4. That bottom number also tells me the number of electrons as well. So it tells me it's got 2 electrons also. Those have each got a -1. Periodic table, we'll start over here. Tomorrow, in the booster and in the exam, just before your exam, I'll show you how to label the periodic table in detail. But for this, we'll just go through the areas of the periodic.
The only thing we can do now is try and get another guess what I found.
It says live now. It's working at HC.
Oh, it's loaded a bit more on my phone there. Oh, apparently it's streaming, but I can't get it on here. What's it saying on there?
And we're live. John.
John says alive.
Just to clarify, is this on?
A little bit of
He knows my name. buffering on mine now. I'm just going to start writing some stuff and then... I can log in.
No, it's still on. Sorry.
Cool. Mixtures. So elements only contain one type of atom. Compounds contain two or more elements bonded together. Mixtures contain two or more elements or compounds that aren't bonded. Then you've got your separation techniques to separate these things out. Got distillation, which is separating two liquids based on their differing boiling points. Fractional distillation, which is where you separate variety of liquids that all have different boiling points. An example would be what you do for paper 2, which is crude oil. Chromatography, again, more likely to come up on paper 2 because it's a big topic on paper 2, but it's where you separate out inks and dyes using a solvent and based on solubility. You've got filtration, which is where you're separating out a undissolved solid from a liquid, and crystallization, which is where you're separating a dissolved solid from a liquid, so like salt from water. Up here, went through the different scientists and the names. So Dalton said atoms can't be broken down. Thomson, who came up with the plum pudding model and he discovered electrons. Rutherford, the only one of the 5 that you need to remember what he did. He did the gold foil experiment, and following that, he realised that the nucleus was positive and there was lots of empty space in the electrons. So looking at this, he realised there was space between this middle bit and where the electrons were. Bohr then said that electrons were actually placed in shells, so he came up with shells. We'll put underneath that actually. So for shells, we've got some maximums, which we've not got on here. So remember, the first shell can take 2, the second shell has a maximum of 8, and the third shell has also a maximum of 8. Just a bit of information there on shells. Chadwick came up last year, I think, on separates, and he discovered neutrons. So then we looked at helium as a quick example. So this is what you'd see on your periodic table, and you might be thinking, okay, what exactly do those numbers mean? So in the middle, we've got the symbol, nice and easy. Then you've got the bottom number, which is 2. Now that 2 tells us 2 things. Firstly, it tells us the number of protons, and it also tells us the number of electrons. Now remember, protons have got a +1 charge, and electrons have got a -1 charge. So a question might say, why is an atom overall neutral? And it's because it has the same number of protons as electrons. Then up here, you've got the mass number. That tells us 2 things added together, and that is the protons and the neutrons. Then I've done a little diagram of an atom. So here for helium, you've got your nucleus, which contains these 4 things. So 2 protons, 2 neutrons. Then in the shell, as Bohr said, you've got your electrons. And I've put the masses for the protons and neutrons there. So the protons and neutrons have a mass of 1, each one contributing, hence you've got a mass of 4 altogether. Electrons mass in your exam is very small, so you can get away with writing 0. Down here, we then moved on to the periodic table. So you've got a scientist, Mendeleev, who ordered them based on masses, and he left gaps for elements, which is why his periodic table was the one that was then used. Then you've got your 3 groups on your periodic table. So alkali metals, halogens, and no. Group 7, 7 electrons in its outer shell. Group 0, full outer shell. And that is why they are very unreactive. For group 1, they're very reactive metals actually, and they get more reactive as you go down the group. And they react vigorously with water, you will have seen. Group 7, they start off reactive at the top, but they get less reactive as you go down. So that's why I've written more and less reactive there. So as you go down, these get more and these get less reactive. Now this bit here is higher tier only, so that you need to understand and be able to explain why that is. So for group 1, they get more reactive because there's less attraction between the positive nucleus and the outer shell electrons. Therefore, the outer shell electron is more easily lost. Now for group 7, you can write exactly the same bit here for your explanation. It's just the ending that changes. So it's the same thing. There's less attraction between the positive nucleus and outer shell electrons. However, it's harder for it to attract 1 extra electron. Because remember, group 7 got 7 in their outer shell. So therefore, they're wanting to gain 1 electron. So it's harder for them to get that one. Last thing to put together, so I sort of stopped them, is metals and non-metals. You just need to understand just be able to name some properties. So I'm going to do metals, and it's the opposite pretty much for non-metals. So metals are shiny, You may use the word lustrous. They're malleable, which means that they can be shaped, and they do conduct electricity and don't conduct heat. So little comparison there. So it brings us up to speed. The last half hour after we've finished trilogy. So I'll move on and we'll pass on to Miss Slow. She's going to...
Right then guys, spec 2. So it's all about bonding, structure and properties. So there's 3 different types of bonding. The first one is ionic, and that occurs between a metal and a non-metal. And what's happening to the electrons is that they are being transferred from the metal to the non-metal. And because of that transfer of electrons, we get a metal that is a positive ion. So we do have ions being formed. So an ion is just a charged particle. So metals are positive and non-metals are always negatively charged. So an example might be something like a sodium chloride and how you would draw that, or if you were asked to complete a diagram on that. So you'd have sodium. It should have at this point a full outer shell of electrons because the electrons have been transferred. And like I said, that will be positive. And if it was chlorine, that will have gained the 1 electron that sodium has lost, and that will become a negative ion. So that's an example of how we would draw that bonding. So we've got high melting points. And that is due to the strong electrostatic forces of attraction. Because that positive and negative, those positive and negative ions are attracted to each other, and that's a strong electrostatic force of attraction. They can also conduct electricity, but that's only when they are molten or aqueous, so when they're liquid or when they've been dissolved in water. And that's because the ions are free to move. So because they're free to move, they can carry that charge through the structure. Now, second type of bonding is covalent. So for this one, it's 2 non-metal atoms, or at least 2 non-metal atoms, and we have got the sharing of electrons. And these ones, they can form small molecules. So things like methane, oxygen, ammonia, or we've got giant structures, which I'll come on to in a little bit. Now, if you were to draw these, I'm going to go for chlorine, which is Cl2. Just need to be drawing the outer shell because that's the only one that is involved in the bonding. Oh. So chlorine is in group 7, as Mr. Addy has just mentioned when going through spec 1. So they've got 7 electrons in their outer shell. In order to get a full outer shell of electrons, they need to gain 1. So what they're going to do is they're going to share 1 each. So we've got 1 electron coming from one chlorine, 1 from the other. So there's 1 each there. We've got to draw the other 6 on the outer shell though. So 1, 2, 3, 4, 5, 6. And then this one also has the 6. Now don't forget that pair of electrons is 1 covalent bond. You can also get 2 pairs, so that'll be 4 electrons in the middle is a double, and you can also get a triple, so that'll be 6 electrons in the middle, which is 3 pairs. These have got low or relatively low melting points. Because there's only a few bonds. And they do not conduct electricity. So that doesn't matter whether they're solid, liquid or gas, they don't conduct electricity because there's no charges. So no ions are formed, it's just the atoms sharing the electrons. Final type of bonding, I'll just go through very briefly, is metallic. And this is between 2 or more metal atoms. Now, if you were to see a diagram of it, you'd have your positive metal ions, because remember, metals form positive ions. They form this nice regular pattern. And in between those, you've got those delocalized electrons, which I'll just show with a negative symbol. So they're just scattered throughout the structure. Just like our ionic bonding, they've got high melting points. Because again, we've got that strong attraction between the positive charges and the negative charges. And they can conduct electricity even when solid. So solid, liquid, they can conduct electricity. And that's obviously due to the delocalized electrons. Now, one other little thing about metals, we can actually have things called alloys. So instead of having a pure metal that might just be made up of one type of metal atom, you can actually mix it with a different, usually metal, but sometimes can be non-metal atom, and this makes it stronger. So alloys are stronger than pure metals. And that's because if you see this nice regular pattern where you've got these metal ions in layers, the alloy, okay, with that different atom in it, it'll be a different size, so smaller or larger, it will distort these layers. So instead of just them being able to slide over each other and bend, okay, it distorts it, so actually it can't bend as easily. Okay, so they are stronger due to distortion or disruption of the layers. So as well as those 3 types of bonding, there's some other structures you need to know about in not as much detail, but you do still need to know their structure and their properties. So just split this into 4. We've got diamond. Now all these structures that I'm going to go through are just made of carbon atoms, so they're forms of carbon. So the first one being diamond, which I'm sure you've heard of. Each carbon atom is bonded to 4 others. And this makes it very strong because there's many, many, many bonds. And remember, because it's carbon, that connects two non-metal atoms, so that'll be covalent bonding. So many covalent bonds make it very strong. They can't conduct electricity. And they've got high melting points. It's one free electron. Okay, and these layers are made up of hexagonal rings. So you've got these carbons, three bonds to each one. They make these hexagonal rings. Those hexagonal rings then form these many layers, many layers. They can conduct electricity, and that's because of that free electron. And because we've got these layers that have strong bonds within them, the layers actually don't have bonds between them. There's just forces holding them together. So they're actually what we'd call slippery. So that's because of weak forces between layers. Third one, graphene. Okay. Graphite, made up of many layers. Graphene is just one layer of graphite, so it's just one sheet of those hexagonal rings. So each carbon is bonded to three others. Again, we've got that one free electron. Hexagonal rings. And it will have the same properties, and it can conduct electricity, but it's very strong because it's just covalent bonds and not layers, with weak forces between them, should I say. Final one, things called fullerenes. So these are usually made up of hexagonal or pentagonal rings of carbon. They're hollow, which is a key factor about their structure. They're very strong. And within fullerenes, we have things called nanotubes. So they're still made up of hexagonal or pentagonal rings, hollow and strong, but these are long cylindrical tubes. Which have a large surface area to volume ratio, which makes them very useful. I think that's everything I'm going to cover for Spec 2. So we're going to go back to Mr. Addy for Spec 3, which is the quantitative chemistry.
Wonderful. Interesting comments there. Sadly not related. So, Spec 3. So, it really boils down to, can you do three things? So, one of them being MR, which looks like Mr. And that all involves using the top numbers. So when you're doing this, use the top numbers on your periodic table. So I'm going to give you an example. So it might say to you, work out the relative formula mass. And that is basically the same as the MR, they're the same thing. Now, the question might say, work out the MR, or relative formula mass, and it might say sodium chloride. And it will give you the symbol, so NaCl. What I'm doing is I'm then looking for the top numbers on my periodic table. So I'm going to sodium and seeing that the top number for that is 23. Go and find chlorine, and I can see that that's 35.5. What all I then need to do with those numbers is do a simple addition sum, add them together, and you end up with that. Depending on what it is, it might be something that looks like this, so it could be H2O. In that case, top number of hydrogen is 1. However, as you can see, there are 2 hydrogen atoms there, so we multiply it by 2. to get 2. There's 1 oxygen atom, which from the top number on the periodic table is 16. Again, simple sum, 2 at 16 would give me 18. So that is relative formula mass, which is the basis really of particularly one equation, which is your moles equation. Now, there are various uses of this in your exam. It might be talking about limiting reactants, might just be talking about how much of, what is the mass of this substance made when we use 55 grams of this substance, but each one will involve the moles equation. Now the way to remember it is mass of Mr. Moles. Now if you remember that, that then sets it out nicely in your equation triangle. So there we've got our equation triangle. So what it might say to us, a simple question might be, what is the number of moles of chlorine when we have 5 grams? So what we would do is we'd take the mass, which I said was 5 grams, we'd divide it by the MR, which we know is the top number for chlorine, exists as Cl2. So I'd say, okay, we've got 2 chlorine atoms there, it's 35.5. However, because we've got 2 of them, quickly times it by 2 to get 71. Put it into the triangle, I do my mass. So 5 grams divided by 71. This would usually be a 2-mark question. And looking at this, I'm getting 0.07 to 2 decimal places. So that is how you go about it. Now that calculates moles. You may have to go a step further or a couple of steps further for a reacting masses question. Now there was one of these on Trilogy last year, but even for a limiting reactants question, you do have to take it a bit further. So it may say, what is the mass of a substance produced when you have 10 grams of, let's say, water or any compound? Again, you just use this equation, but you cycle through it twice. So it just depends on what the question's asking you. But if you can remember this equation, use the numbers available to you. If there's a mass there in the question, use the mass. You know you can work the MR out at any given time because all you're using are the top numbers on your periodic table, and you just put it into that triangle. It's a very straightforward question, and they're worth usually like 4 marks. So it's a really quick way of picking up some easy marks there. Another equation that you need to be aware of is the concentration equation. This comes in 2 forms. So there's, for separates later on, we'll look at the separates version, which involves moles. But for everyone else, it's dead easy. It's just a case of mass divided by volume. So straightforward. So if we were to put that into a triangle, we put mass again at the top, volume here, and concentration underneath. And again, you've got your triangle. Now, the thing to remember for this one is the volume. Now, this has to be in decimeters cubed. Now, if with it being in decimeters cubed, you have a bit of a conversion usually to do within your answer. Now, 1 decimeter equals 1,000 centimeters cubed. Now, the most common volume I've seen in questions is usually 25 centimeters cubed. So what students will do is they'll go, okay, it tells me that I've got 5 grams of something and I'm dissolving it, so I'm just going to do 5 divided by 20. Wrong. You need to convert this volume first into decimeters. Now, if 1 decimeter is 1,000 centimeters cubed, we're going to have to divide this by 1,000 to get it into decimeters. So therefore, that would actually be the volume that I would use. So a really important point, if there's a concentration question, check the volume given to you is in decimeters before doing anything with the numbers. So really important, and it's such an easy thing, and you get a mark for it as well. So just converting it, just dividing it by 1,000, because almost certainly if there's a question tomorrow on any paper involving concentration, they'll give you it in centimeters cubed. First thing, convert it. A few extra things to bear in mind for Spec 3. I'm not going to spend much longer on this. But you've got conservation of mass. So I'm just going to talk about these really and just give you the words. So conservation of mass, there's a definition. That's really a definition. So that just says that no atoms or mass can be gained or lost during a reaction. So that's your conservation of mass. You will have spent a lesson on it. You've got uncertainty. And this is all to do with chemical measurement, so how accurately we're measuring things. Now, there is a way of working out the uncertainty or giving the uncertainty in an answer. And what you need to have is, firstly, you would write the mean, and that would go in the answer box like that. So that would be your answer. You'd have to probably calculate a mean, and it'd say, give the uncertainty. And then you'd see this symbol, which is plus or minus. Now, after that, you then have to do half of the range. So half of the range. So for example, do a little quick example up here. So let's say our numbers are 5, 6, and 7. I'm going to add those together. So I get 18. I then divide it by 3. And I get back to 6 again. So I would put 6. The range is the highest minus the lowest, so I'd end up with 2. But remember, I'm doing half of the range. So plus or minus 1, and that would be how you represent your answer. The only other topic that comes up in Spec 3 is gases, and it's reactions involving a gas. So what you're looking out for is when you've got a symbol equation, and it might be, let's say you've got sodium reacting with an acid. So we put in some sodium there into some hydrochloric acid. What you'd find is you'd end up with some sodium chloride and you'd get some hydrogen gas given off. It might say to you, why would the mass appear to decrease in this reaction? And you might think, okay, we've got some sodium, and you'd get a little S there. You'd see the AQ symbol, which we know stands for aqueous. You'd see an AQ there, because you know it stands for aqueous. Next to hydrogen, you'd see a little G. That stands for gas. And what that's telling, the clue would be there in the question. What it'd be saying to you is, oh, there's some hydrogen gas being produced. That would be being released from the container, so the mass would appear to go down. And that is pretty much it for Spec 3. As I say, these are your 3 main bits. This one in particular, and I didn't mention this before, that is higher tier only. So if you are doing foundation, this and this and these things over here could come up on yours. Moles though, so this equation particularly could come up on higher, and it's higher tier topic. So it's almost certain that they'll ask a moles question, and using that a triangle just depends on how they want to represent it. Okay, pass on to Miss Slow, who's going to go through Spec 4.
Right then guys, Spec 4, quite a long one, lots of content in there, especially when it comes to the electrolysis. Now there are a couple of, a key couple of practicals in there which you have done plenty of sort of revision and work with. So I'm not going to go into too much detail over those. What you do need to know are the reactivity series. So if you haven't had chance to have a look at that yet, then you definitely need to go and learn that tonight, because you're not given that in your exam. Basically, it's group 1 up near the top, then group 2, then group 3. Then you've got carbon, you've got your transition elements, you've got hydrogen, and then you've got things like copper, silver, gold, so sort of your jewellery metals at the bottom. That's probably the easiest way to try and remember that. Now, couple of different reactions. So we can have reactions with metals and water. So you get your metal, react it with water, and you will produce a metal hydroxide plus hydrogen gas. Okay. You can also have metal reacting with oxygen, which will produce a metal oxide. You can also have a metal reacting with an acid, which produces a salt, and I'll come on to those in a second, plus hydrogen, again producing hydrogen gas. And then you can have an acid and an alkali, which again produces a salt. but this time you get water. So that one is known as a neutralization reaction. So salt. What I mean by that, it's made up basically of two words. It'll be whichever metal you have used, which will come from the alkali, and then it will either end with chloride, sulfate, or more rarely nitrate. I can imagine the ones that come up in your exam will either be chloride or sulfate. The chloride will come from hydrochloric acid, sulfate will come if you've used sulfuric acid, and you will always produce water in those reactions. Did a little bit about pH scale. I will just say acids, they contain H plus ions. Neutral will contain an equal concentration of H plus and OH minus. Alkalis contain a high concentration of OH minus ions. We've also got displacement reactions, which, like I said before, you need to know that reactivity series. So displacement is simply where a more reactive metal takes the place of a less reactive metal. So if I just give you an example, we might have something like copper sulfate reacted with potassium, which is the most reactive metal you need to know about. Apologies, I'm going to write this underneath rather than on one line. What would happen, because the potassium is more reactive than the copper, because they're the two metals in this equation, that's going to take the place of the copper. It's going to swap because this has a higher affinity to react to that sulfate ion that is present. So you'd actually get potassium sulfate plus copper. Okay, so now you're left with copper on its own. Right, electrolysis, I'll quickly go through. So there's two types of electrolysis. You can have molten, so that's just you've melted down your substance, so it's liquid, or you can have aqueous, which is mentioned before, is just a substance dissolved in water. Now when it's molten, you will get two ions that are in the substance. So I'll just mention electrolysis is for ionic compounds. And you've got two electrodes in that, which you should be aware of. Easiest way to remember which electrode is which is the word panic. So positive anode, negative is cathode. And because the anode is positive, it will always attract the negative ions, which, as I said when I was going through spec 2, will always be the non-metal. So the non-metals are always attracted to the anode. The negative cathode will always attract the positive ions, which will always be the metal ions. So in molten, you'll have your metal ion, which is positive. I'll just pop that in brackets. And at the anode, you'll produce your non-metal ion, which will be negative. So that one's nice and simple. When it comes to aqueous, because you've also got water present, you'll not only have the metal ion, you'll also have the H plus ions that are contained in water, because if you remember, water is H2O. You'll get the non-metal ion, which is negative, and also OH minus. Okay. So here I'll just put this as the cathode, and this is the anode. So at the cathode, your choices are producing the metal. So this will probably be something like copper, silver, or gold they might mention. So if they're mentioned in electrolysis, then they will be produced at the cathode. If it's not, If it's one of the more reactive metals, then you will produce hydrogen gas, and you'll see that because it is a gas, it will produce bubbles, whereas the metal will produce a solid in the solution. At the anode, where you can get the non-metal or the OH minus ions, you will either produce oxygen, oxygen gas, or you will produce probably more than likely chlorine, but any halogen. So it could also include bromine, and potentially might mention iodine, but I can imagine the more likely one they would use is chlorine, but just bear in mind it could be bromine as well, any group 7 halogen. So it will be oxygen unless the substance that you are running through electrolysis contains chlorine or bromine, in which case they will be produced over the oxygen. But if you're looking at this on a diagram, both of those will produce bubbles because they're both gases. So the way, obviously, you need to remember these rules, either oxygen or chlorine. I think we're going to stop there for spec 4, so we can move on to spec 5. So back to Mr. Addy.
So, spec 5, quite a straightforward one. What I would say, last year not many questions on this, and I'm going to go to town on a required practical because that's my prediction, particularly for trilogy, as it didn't come up at all last year. So, firstly, spec 5, you've got exo and endothermic reactions, and everything is based around that. So, exothermic and endothermic. That's what it's all based around. Now, in terms of how to remember what the definition is for each of these, if you remember, energy exits in an exothermic reaction and energy enters in an endothermic reaction, then you can't go wrong, really. But exothermic releases energy to the surroundings. Endothermic absorbs energy from, so releases to the surroundings, absorbs energy again to the surroundings. So that would be your definition for each one of those. Now, because of those definitions, you then need to be able to understand, you're expected to be able to understand some energy level diagrams or energy profile diagrams. Now, I'm going to draw two sets of axes rather, and put on some information onto each one. So first I'm going to draw exothermic. Now, exothermic's releasing energy to the surroundings. So what's going to happen is you're going to find that you start off up here with your reactants. You have a little bit of activation energy, and as you can see, the energy decreases on the diagram. For endothermic, it's the opposite. So it starts off lower. Again, you have your activation energy, and it ends up further up. And this would be your endothermic version. Now, you might be expected to label each of these. So firstly, this bit here would be reactants. This bit here would be products. And then it'll be the same on this side. So again, you've got your reactants, just put the letter and products. Then you've got a little hump bit on each one. Now that, as you can see, always starts from wherever the reactants start at. So whatever the level the reactants start at, that is where your activation begins. And it always reaches the top of this hump, as you can see on the diagram. So that is called your activation energy. They may ask you the definition, and it's the minimum energy needed to start a reaction. So minimum energy needed to start a reaction. You may also be expected to label this part. So as you can see, starting at reactants going up to your products this time. Now that is your energy change. Sometimes you're expected to finish these off, really. I think that was a question last year. So what they might give you this time is a completed one, and they might label all these parts. So they might say, label this A, B, C, and D. And you'd be expected to say, okay, A is the reactants, B is the products, and so on, and basically finish off the diagram for them. Now, for higher tier, For higher tier, you need to be able to understand the energy changes, and that involves bond energies. Now, on paper, well, on chemistry, on the chemistry papers, 20% of it is maths content or maths skills. So therefore, I think for trilogy, they could ask you, one of your calculation questions could actually be related to bond energies, because they didn't ask that last year on trilogy. So therefore, it could come up this year as a question. They tend to be 5 marks. Now, when you're doing that, it's based on the data you're given in the exam. So in order to do this, you have to use what they give you. But it's all about adding up the bond energies within each of the reactants. So just an example, you've got A plus B produces C. You'd add up the bond energies firstly on the left side, so you add all these together. You then add up the total for C, and you do reactants minus products. So your arrow turns into a takeaway symbol or a subtraction symbol, and you do reactants minus products. Now that'll generate an answer. If it's positive, it's endothermic. If it's negative, it's exothermic. And what that means is there's more energy in endothermic reactions going into the breaking down of bonds than there is in the making of bonds. If it's negative, it's telling you there's more energy going into the making of bonds than there is in the breaking of bonds. And therefore, you may have heard your teachers mention this made-up word, bendomex, which stands for breaking is endo, making is exothermic. So again, higher tier stuff only. If you're on foundation, then it's just this top bit, understanding the definitions and how it relates to this. Now, I did mention a required practical. So temperature changes. Now, for this practical, in terms of the types of question that you might be asked, I think really it boils down to, do you understand the method? Do you understand the variables in particular? And if you do, then you'll be able to answer each type of question really. So in terms of the method for this practical, we firstly add a set volume of acid to a polystyrene cup. So that is actually going to be your control variable. So within this practical, you've got your control variable there straight away. You use a polystyrene cup because it insulates whilst you're doing this. So you add a set volume of acid to a polystyrene cup. They may name the acid for you, so just use the acid that's given to you in the question. If not, go with something sensible like hydrochloric acid. What you then do is measure the start temperature. And you record that, so measure the start temperature. And then after that, you then add 5 centimetres cubed of whatever the alkali solution is, probably sodium hydroxide. So you add 5 centimetres cubed of the alkali, and again, measure the temperature. Now, when you add an alkali and an acid together, it's an exothermic reaction, hence it's linked to this topic. So whilst you're doing this practical, you will notice that the temperature on your thermometer starts to increase. In terms of your equipment setup, so here's your polystyrene cup. Here you've got your acid inside. On top of it, you always put a lid, and the reason that you should put a lid is to further insulate it, preventing any energy being released from your polystyrene cup. So in here, you'd start off with your acid, which would be your control variable, because you're keeping it constant. You then measure the temperature. That is going to be your dependent variable, because that is the thing that you are measuring throughout the practical. And then you are changing the volume of alkali, which would be sodium hydroxide. And you'd keep adding, you'd add 5 centimetres cubed, then you'd measure it. Then you'd repeat it. So you repeat that, and then add another 5, measure the temperature, add another 5, measure the temperature, and just keep going. Now, you'd then reach a point where your temperature would initially, on a graph, it would start to increase. And you might be asked to plot some results for this. So you might be asked to plot some results and you'd notice it would be increasing. However, you'd reach a point where all of the acid would have fully reacted and the alkali would now be in excess. And therefore, because this might be up here, maybe like 40, 50 degrees. Now, if you're doing this at room temperature, which is around 20, that alkali you're adding is actually at room temperature and all the acids reacted. So you would then start to see the temperature falling. And in terms of plotting your graph, it's a weird one. Rather than doing a line of best fits like a sort of smooth shape, you'd actually draw it like that, where you have one line of best fit going up and one line of best fit decreasing. So like I said, in terms of questions for this, they may ask you to plan it as a method, which I've seen before, of a similar type of question. They may ask you the variables involved or to include those in your method. So you've got your independent, which is thing you're changing, which is, as we've said, this one. So we'll put independent there if you're wanting to play this back or pause it. So that's your independent variable, the volume of alkali. You're then measuring the temperature, so you measure that, and again you're measuring the temperature each time, so that's your dependent, that's your measurement, and your control variable is that volume of acid that you are keeping constant throughout. So that pretty much brings to an end all of Trilogy. We've not gone, as you know, we've not gone through absolutely everything, but we wanted to just go through the real main key things and some of the skills that you need to be able to answer those questions. That's it. So in terms of Trilogy, we've now finished. So we are going to move on now onto separates. I'm just going to have a couple of minutes and then we'll move on. We will leave it on though. Okay, we're going to move on now to separates. So if you are doing foundation separates, then you still need to be aware of each of these things. It's just that we're going to run through it now, so it mostly hits higher tier people. Anyway, spec 1. So spec 1, transition metals. You'll have done maybe 2 lessons if you were lucky in year 9 on transition metals. This last year on separates came up. They usually like to ask a question around comparing it with group 1. That's exactly what they did last year. Do I think it'll come up this year? Doubtful, but there aren't many separates only there isn't much separates only stuff for this exam, so they ain't got slim pickings really for the examiners. So transition metals. Firstly, as I say, comparing them to group 1, they've got a higher density. They've got a higher melting and boiling point. Stronger and harder. So you think of a group 1 element, your teachers will have chopped into them with knives. So there's not many metals you can cut in half with a knife, whereas you can with transition metals. In terms of reactivity, they're less reactive if you put them in water. So with water, oxygen, and also any halogen. So chlorine. Now they have some uses, so they could ask you around the uses. I think the question from memory last year was all about a 2-marker comparing it with group 1. So they might ask you transition metals this year around uses. So catalysts is one use. So they're used to speed up reactions. We've also got they form coloured compounds, so that has its uses. So they can use the coloured compounds for different things. If you're wanting something that looks like a bluey colour, you might use copper, depending on what it is. And then you've got more than one type of ion. It's not necessarily a use. Just put a little line between it. They also form more than one type of ion. So an example would be Fe2 plus and also Fe3 plus. So that's spec 1. For spec 2, again, this is a really small topic, but this did not come up last year. So this, put a little line around that so we know that that's something separate. So spec 1, spec 2. Basically, this is all about comparing the size of atoms and also then particles. Now, it's worth noting that an atom, in terms of size, is roughly 0.2 nanometers in diameter. So if we were writing that in standard form, so this is where a bit of standard form and a little bit of maths might crop up in your exam. So you've writing that as standard form would be 2 times 10 to the minus 10 meters. So fairly small. Nanoparticles. So a nanoparticle, by definition, is anything which is 1 to 100 nanometers in diameter. So if we were writing that in standard form, it is 1 times 10 to the minus 9 meters, and the 100 nanometers would be 1 times 10 to the minus 7 meters. So there are some uses for these, and I'll just note just 2 or 3 down, just as some examples. So they may say, what are some uses? What they could do to sort of get your nanoparticles into the exam, because as I say, one question last year, they might slot in a standard form question around the size of it, in comparing it to atoms, and they might get you to do the standard form, which is part of one of your math skills for all your GCSEs in science, that is. And then they might say, give a use, or give a couple of uses for them. So, and for this, there'll be many options. So you can use them to deliver drugs in medicine. So because they're so small, you can get them into the body easier, and therefore for drug delivery. You've got in electronics, because they're so small, maybe all right, 4 or 5. You've also got in cosmetics. You've got sun creams. And you've also got as catalysts. Now, again, linking on from catalysts, the reason they make good catalysts is because they are so small and it would give them a higher surface area. So that is your spec 2 separates. Now, spec 3 is all based around different equations. I might finish off with spec 3 and get another sheet for 4 and 4 and 5. But for spec 3, you've got percentage yield. There was a question on each of these separates calculations last year. So trying to predict this is quite hard because they've got to, as I said before, put 20% of the marks going into math skills and things. So what they might be tempted to ask you about it might be, again, just utilising these again. So they might just go percentage yield, percentage atom economy and concentrations. They might go for something they've not asked before, which we might be using the moles equations and put it in that way. Now for percentage yield, what you do is you do actual yield divided by theoretical yield. That gets you a number. Now your actual yield will always be less in this sort of question than your theoretical yield. So that will be a number less than 1. So it'll be at 0. Whatever. Now you then take your answer. Because we're wanting it as a percentage, we multiply it by 100. And that turns it into a percentage. Very straightforward question, that one. Then you've got atom economy. Now for atom economy, it's all about working out how efficient a certain reaction is at producing a desired product. So you might be wanting to produce, let's say you were looking at photosynthesis, and it was all about how much glucose was being made during photosynthesis. And you'd look at reactants and products and pick out the one that you're wanting and then make a comparison. Now there is an equation for that. So what you would do is you would firstly work out the mass or the relative formula mass, so I'll put MR, of the desired product. So like I said, plant's desired product would be glucose in photosynthesis, so that would be my desired product. And what I'd then do is I would divide, I'm going to divide that by the relative formula mass, or MR, whichever way you want to, whatever you prefer to look at or call it, of all the reactants. Now you may have learnt this, which is relative formula mass, or MR, of all the products. It doesn't matter whether you do all the products or all the reactants, you will get the same answer. That again will generate a number which is, it could be one, because there might only be one product. It's more likely that it's going to give you a number less than 1, so 0 point something. So it's going to be 1 or less. And again, with that one, you take your answer and you times it by 100. And then another equation that you need to be aware of is your gas volumes equation. Now this one is all about understanding the volume of gas. So I'll just put gas volumes. At room temperature and pressure, which I'm going to call RTP, is 24 decimeters cubed. Now remember, your conversion for converting to decimeters could come into play. 24 decimeters cubed, let's think, would be 24,000 centimeters cubed. So important little point there. So for this one, you might be given a gas to work out, and you'd be expected to work out what would be the volume of gas at room temperature and pressure. So what you would do is you would do moles times 24, and that would give you its volume of gas, feet volume of gas. There we go. Units for that again would be decimeters. Now last year this was a question right at the end, so concentration. Slightly different to the trilogy version of this, so it's about understanding the triangle. So if you remember mole vol conc, which is moles, not vols but volume. I had vols in my garden last year, nightmare. Concentration, and there we go. So mole vol conc, can't go wrong. And that'll help you work it out. Now moles speaks for itself. Volume again needs to be in decimeters cubed. Concentration this time is in moles per decimeter cubed. Now previously the trilogy version was grams per decimeter cubed, whereas this one's moles per decimeter cubed. So just bear that in mind. Look at the units. I know in physics, one of the key ways of working out what equation you're using is all based around the units, and then using those to suss it out. So yeah, just sort of work it out whether you're using this equation or the previous one. For this, they asked a big 5-mark question on this related to a titration. They didn't give you the method for titrations. They just talked about using this equation. One thing that you sometimes have to do is look at a ratio for an acid and an alkali if it's a neutralization reaction. So just bear that in mind. But if you remember this equation and you use it properly, you can't go wrong again. So check the volume that you're given, make sure it's converted to decimeters cubed. I'm not going to put that conversion on again, but because I've done it twice. But remember, 1,000 centimeters cubed in 1 decimeter. So convert that first. You probably will be given a concentration of one of them. That will allow you to work out the moles. When you've got that, you then divide that by your volume for the other substance, and that is how you work out your concentration. So again, a few steps for that. But like I said, it was questioned last year, so I don't want to spend too long on it. So the one I do want to spend a little bit more time on is titrations. So spec 4. Your main, or your only, separate bit of content is a titration. Now, this could be a prelude to a concentration question. So in order for them to get the maths in there, what they might do is they might firstly put a method in about titrations and they get you to do the calculation. But the method for titrations is based around reacting an acid and alkali and understanding at the point at which it is fully neutralized. So in order to do that, you need set equipment. So here you've got a clamp and a clamp stand, and in there you'd have a burette. There's my burette. Underneath you would have a conical flask, and that conical flask would be sat on a white tile, and you'd be almost ready to go. There's my tap. Now, once you've got this equipment set up, what you'd then be expected to do is firstly fill the burette up to 0 with acid. Now, you might be expected to name an acid. Again, pick something sensible, pick hydrochloric acid. If you're given an acid in the question, might say sulfuric, might say nitric, then just go with whatever's given to you and put that into your burette. What you're then going to be expected to do is mention measuring out a fixed volume of alkali. So this is going to be your alkali. Make sure you measure fixed volume. Pick something sensible, maybe 25 centimeters cubed. Put that in there. That's going to go into your conical flask. So that's a conical flask, conical, cone shaped. Here's your white tile. So here is your burette. Now, to load your burette with hydrochloric acid, you'd use a funnel. So you'd need a funnel to get that into there accurately and get it up to 0. That needs to be shut. Then you put your alkali in here with some indicator. So they would probably give you the name of the indicator they're intending on you using. Now in school, I know we've used a couple. We've used phenolphthalein and we've used methyl orange. So a couple of examples. Let's see if I can spell this right. So phenol, there's an L and then PHTH, phenolphthalein. I'm pretty sure that's right. And also methyl orange. That's easier to spell. I think the required practical actually uses methyl orange, but you could be expected to mention using phenolphthalein. They're more likely to give you that indicator information, to be fair. And make sure that that goes in with the alkali. Now, what you'd then do is you'd open the tap and you start to trickle through some acid into the alkali, swirling the flask as you go. So make sure you mention swirling the flask. You get a mark for saying that because you're suggesting that you are mixing the acid and the alkali. Now, you would stop this tap, so it stops when there is a colour change. At that point, you'd then measure the volume of acid. So that'd all be about taking a reading from your burette and saying, okay, we've used 15 centimeters cubed of acid or whatever it might be, and you measure that. After that, you'd then complete this again. So it'd all be about repeating this experiment a few times, so 3, 5, pick a sensible number, and then after that, because you've got a series of numbers, what you can then do with that is calculate a mean. So to run back through the practical, setting up the equipment gets you maybe a mark, mentioning having the acid in the burette and the alkali indicator in the conical flask placed on a white tile. The reason a white tile is used, if you had to analyse some of these bits of equipment, is so that you can easily observe that colour change, so it's nice and straightforward for you to see. Then you add your acid into your alkali, swirling as you go until you observe a colour change. At that moment, you straight away turn your tap off and record the volume of acid. You repeat it a few times and then you get a mean. For titrations, my prediction is they're going to ask you to write out a method, and they might even afterwards ask you to then do the concentration calculation for it, so using the concentration equation. There's a bit of a prediction from me, might be wrong, tell me tomorrow. So, last one is Spec 5. So Spec 5, last year, I keep talking about last year because I think it's important, but for Spec 5 there's only 2 bits of information really. Whoops, paper knocking about. There we go, shift this out of the way. We're settled. There we go. So for Spec 5, there's only 2 bits really. You've got fuel cells and cells and batteries. Now, last year, a 6 marker on separates was based around fuel cells. So I'm not going to spend too long going over it, but it's all about reacting hydrogen and oxygen to produce water. Now, if we were to balance that, you can see firstly we've got 2 oxygens there, so we stick a 2 in front of that. That gives us now 4 hydrogen atoms, so we put a 2 there. And it's all about this reaction. So it's supplied with fuel. It's a little bit like electrolysis because you have electrodes. So in terms of what one of these things looks like, here you've got an anode, here you've got a cathode. Now, hydrogen comes in like here, and H2 passes into there. This side, you've got some air coming in. So air comes in here, and you have O2 going in there like that. This is your electrolyte in the centre, this middle bit. And during that, what happens is you have some hydrogen coming in. Any unreactive hydrogen goes back down and loops round in the fuel cell. Your air comes in, the oxygen from the air, some of it drops into there, and then what you then get coming out of this electrolyte is water. So a good thing, an advantage of fuel cells over using normal fuels is that you're getting water as a product rather than, say, carbon dioxide, which leads to global warming, etc. You get a constant voltage, and it doesn't run down if the fuel is continuously supplied to the fuel cell. But as I say, they asked the question on that 6 marker last year using data, and you had to use your own knowledge. So they might ask you more around the intricacy of how this works maybe this year. But I'm not sure whether they'll ask a question on it, to be fair. Cells and batteries. So my classes will remember, I plonked you an orange and said, go forth and generate voltage. And you looked at me like I was an idiot. But it's based around metals and the difference in their reactivity. So the difference in their reactivity. So for example, if you've got, you hear lots of, you see these adverts with that pink bunny on it, with that Duracell t-shirt on it, and it talks about lithium-ion batteries, and that's because lithium, as mentioned earlier, lithium is near the top of the reactivity series. It's in group 1. So that's near the top. Now, the other metal often found in batteries would be copper, which is way down. So 4th bottom on your reactivity series. And that difference in reactivity is what generates the voltage. The greater the difference, the greater the voltage generated. So therefore, that's why companies often use lithium, because there's a big difference. It's not as dangerous as banging potassium in a battery, where if it got wet, it'd start blowing up in your pocket if you had a phone. So therefore, use lithium, and therefore it generates that voltage based on that difference. Couple of advantages. It's portable, hence you'll understand that. You've all got phones. You're probably watching this on a phone now. It's rechargeable, so if you plug it in, it'll reverse the process, and we'll look at why it produces electricity in a second. And also it's difficult. However, they are difficult to dispose of, so you might know that you have to take batteries to shops to get them recycled. Now, it all works on the principle of oil rig. So, whoops, that's an R. Let's write that again. Oil, I can spell. Oil rig. So oxidation is loss, reduction is gain. So you may have remembered this before. So this is all about electrons. So in a battery, what's happening is there's lots of oxidation. So the electrons are being lost, and they're going into the circuit, producing, running through the light bulb or whatever it might be. You're powering in a torch or something, and then you've also got reduction going on at the other end. Now, in a rechargeable battery, this process is reversed using mains electricity, and that reverses it, and therefore you can then use that battery again. But that pretty much sums up cells and batteries. So that brings us to the end. We're a little bit later than scheduled, but we did have a few technical difficulties. Internet's down, and a few issues. What I would want to just mention to you now, or I do want to mention, is there's a booster tomorrow at 8 o'clock in the morning. If you come to that, we'll be running through some of this information again, a few extra skills on how to label periodic tables and stuff to think about going into your exam. Again, laying it on thick about these required practicals that we think may or may not come up, particularly temperature changes for trilogy and maybe titrations for separates. So 8 o'clock tomorrow, and remember, after that, you've got a bit of time, and then you've got your exam start in the theatre again, going through some last minute stuff before your exam. So make sure you are on time for your exam. Okay, thank you for watching.